Hello, and welcome to today's webinar, Advances in Unmanned Aircraft, AI and Autonomy, Threats, Countermeasures, and Opportunities. I'm Amanda Hosey, your moderator for this 60-minute program from the editors of Aerospace and Defense Technology magazine. Our speakers today are Jason Hardy-Smith of Iris Automation, Rich Ronsky of Charles River Analytics, and Jeffrey Starr of D-Fend Solutions. Before we begin, I would like to thank the sponsors who made this webinar possible: Cinch, Eagle Picture, Maxon, Sea Level, and Siemens. You may download technical papers from each sponsor, as well as PDFs of speaker slides, under the Event Resources tab on your screen. If you have questions for our speakers, please send them through the Ask a Question box, and we'll address as many as possible after presentations. Our first speaker today is Jason Hardy-Smith, who serves as Vice President of Product for Iris Automation, where he leads product strategy, definition, and requirements for the company's CASIA Detect and Avoid portfolio of products. He has more than 20 years of product management experience. Welcome, Jason.
Thanks, Amanda. Good morning. First of all, I'd like to thank you, Amanda, and all of Aerospace and Defense Technology magazine for giving me the opportunity to present today. And thanks to the audience for taking the time to come and listen. Much appreciated. Today, we're going to be talking about how artificial intelligence and autonomy have driven advances in unmanned aircraft. It's going to be kind of broken into three parts. We'll start by talking about how artificial intelligence-based systems can autonomously detect air traffic, take command of the autopilot to avoid that traffic, then allow the aircraft to continue on its journey. Talk a bit about how this has helped drive progress in flying drones beyond visual line of sight, or BVLOS, and how it's eliminating the need for pilots in the aircraft and also visual observers on the ground. I'll then hand over to Rich Ronsky from Charles River Analytics. Rich will talk about how trust and resiliency of autonomous teammates can make missions more successful, and how AI and computer vision can drive better decisions, and also talk about how evolving capabilities of autonomous swarms. Last but not least, Jeffrey Starr from D-Fend Solutions will talk about drone threats in sensitive environments. So, we're talking about that bad actor with a drone flying into a football stadium where there's tens of thousands of people in attendance, and how some of the more traditional counter-UAS solutions are less than ideal. So with that intro, let's get started on how artificial intelligence and computer vision can make the airspace safer and ultimately prevent two aircraft from ever colliding in midair ever again, and also how it can empower UAS to truly fly BVLOS. So I think a good place to start is, why would we want to fly drones BVLOS or beyond visual line of sight? If you look at some of the use cases on the screen, pipeline inspection, railway inspection, drone as a first responder, a lot of these things have traditionally been performed by helicopters or small planes. But, I think we all know, we'd all agree that flying aircraft at low altitude is dangerous, right? Low altitude strikes can cause fatalities. If a small plane has an engine failure when it's flying really low, it doesn't really give you, the pilot, much time to glide and find a suitable landing spot, right? It's also really, really expensive to do this kind of work with helicopters and small planes. The cost of the aircraft, also fuel, maintenance, paying the pilot, insurance is a big one too, right? Drones have started to take over some of this work, but the reality is that today most of it gets done within line of sight of the drone pilot or the visual observer. This means they can't really fly that far, right? Usually you're driving the truck with all the gear inside it to the pipeline, unpacking the truck, setting everything up, flying your drone a couple of miles, bringing it back, packing up the truck again, driving a few miles down the road, and repeating the process. And, granted, that's a lot safer than flying a helicopter, and it's much cheaper than flying a helicopter, but really it's still not that efficient, right? To be efficient, we want to go and let our drone fly 5, 10, 20, 100 miles, right? and gather all that great data as it does it and process that data really quickly, even in real time. And technically, there's no real reason why we can't go and fly that drone 100 miles, right? Drones now have much longer endurance than before. Like, batteries are much better. Autopilots have been capable of doing that kind of stuff for, a long, long time. So why can't we, right? It really boils down to safety. When pilots have to be able to see and avoid other aircraft in the airspace, they have to remain well clear of the other aircraft. And drones are really small. Pilots often can't actually see them, and if you can't see them, they can't avoid them, right? And then, if you have a remote pilot flying a drone, if they can't see their drone, they've got no idea what the drone might fly into. Drones are usually the most maneuverable aircraft in the sky. So if they come across something much less maneuverable, pretty much the onus is on the drone to get out of the way. So think of a drone coming across a hot air balloon. Hot air balloon can't avoid anything, right? It's at the mercy of the wind. So the drone would have to get out of the way. But the same thing kind of applies to anything else, like paraplane, glider, etc. So how do we solve that problem? Turns out that it's actually a pretty difficult problem to solve, right? How can we help that remote pilot to actually see everything and avoid everything when they can't even see their drone? So, if you think about our skies, there are cooperative and they're non-cooperative aircraft, right? The cooperative aircraft are those with, transponders or broadcasting ADS-B. These aircraft are really, really easy to detect and to avoid, right? You just need an ADS-B receiver, and you can see things many, many miles away. The problem of the non-cooperative aircraft, those without ADS-B out, right? So here, for example, we have a paraglider, right? Flying around about the altitude of your drone operation, no ADS-B out, no radio, doesn't make much noise. And there are many kind of aircraft that would fall into this category, right? Hot air balloons, crop dusters, sport planes, gliders, Cessnas, military helicopters, tons of aircraft like that. In fact, it's reckoned that, perhaps as many as 70% of aircraft, I've heard estimates, from between 30 to 70% of aircraft in the US are non-cooperative. So if we want to be able to detect these aircraft and fly really far autonomously, putting technology on board has started to more recently be proven to be a good way to solve this solution. Artificial intelligence and machine learning solutions have been used to create computer systems that can perform tasks that, normally would require, or, historically would require human intelligence. This is done using a variety of techniques, kind of like in the same way as we teach babies how to learn colors or recognize objects or specific toys and things like that. And we essentially train the system by giving it a lot of data to recognize planes, helicopters, multirotors, birds, and distinguish them from any other moving objects like clouds or contrails or trees blowing in the wind or trucks on the ground. And so, using such technologies on board the aircraft can allow you essentially to see, detect, and avoid any aircraft and prevent mid-air collisions. So the artificial intelligence will detect the aircraft, then it can autonomously command the autopilot to change course and avoid that intruder. And once avoided, allow the UAV or whatever aircraft it's on, could be an air taxi, could be a general aviation aircraft, to resume its journey. This essentially is allowing the aircraft to remain well clear of any other aircraft and avoid mid-airs. On the left is the example of an AI system, computer vision solution, and it's from Iris Automation that I work for. So how this system works is, there's machine vision cameras positioned around your aircraft. Typically, about 5 cameras will give you 360-degree field of regard around the aircraft, and they're streaming high-resolution video to a high-powered graphical processing unit on board. and this allows that video to be processed in real time by deep learning algorithms. The system is looking for things like movement, for straight lines, shapes that resemble aircraft, and it can classify them with a high degree of success and understand where they are in the airspace. The drone on the right-hand side is from a company called Aerospace Technologies. You can see they have a single camera, artificial intelligence-based system integrated into the nose of their drone. This has actually provided them, a lot of success in getting BVLOS and EVLOS waiver approvals from the FAA. So, putting those systems on board drones is definitely, pretty good option. We've seen a lot of progress there. Sometimes you want to preserve that payload, for example, to deliver packages, right? You want to deliver as big package as you can, and the more equipment you add to the drone, that's taken away from the size of package you can deliver. Sometimes also drones are just too small to be able to carry a detect and avoid system. So think about something like those little Skydio drones that you see. They're pretty tiny, right? And so for these kind of cases, you can use similar artificial intelligence ground-based systems and to create a sanitized airspace above your drone operation. Here's another example of electro-optical system called Cassia G. This is a passive sensing technology, right? It's electro-optical, and this means you don't need approval from the FCC like you do for a radar. If you have it on the battlefield, it also won't tell the enemy where you are, right? It's a really low-cost alternative to having visual observers. Hardly uses any power less than kind of a traditional light bulb. And you can daisy chain these together for long line linear inspections, or you can do a mesh of them to cover a city. So we see some police departments starting to do that. And you can also co-locate it with a drone in the box to replace visual observers and perform, UAV operations autonomously. When you have these kind of systems, they're obviously going to output data. I think they're basically sensors, you could think of them as. And so how do you view the output of those sensors? Here's a situational awareness tool from a company called Kongsberg. They're taking the output from one of these artificial intelligence-based detect and avoid systems, and they're displaying on the left-hand side, you can see that red kind of toroid shape. That's the field of regard of that detect and avoid system. And then you can see the altitude, the direction, the velocity, position of those intruder aircraft represented graphically in real time through these systems. So this all sounds great, right? But how well do these AI-based systems actually perform? I think it's interesting to start by looking at how well we humans see and avoid other aircraft, right? So think about a human pilot. They actually can't see that much of the sky, right? A lot of it's obscured by the cockpit and the aircraft, the instrument panel and so on. But human eyes actually can't focus on much of the sky at a time. It's only about 2 degrees. So, as humans, we have to perform this kind of scanning technique where we break the sky down into blocks and we look side to side and up and down each block and then move to the next block. And this takes about, around about 20 seconds. But the pilot has a lot of other things to do, right? They've got to check instruments, flight plans, talk to ATC. So I don't know. I mean, it's anybody's guess really, but you probably scan the sky maybe once a minute. And we generally accept, and the FAA generally accepts that this level of performance is safe and fine, right? But we do still have mid-air collisions, right? So let's actually compare human and AI. So, from a human perspective, obviously, we see the pilot's view is obstructed. But if you're a pilot or a visual observer on the ground, you're going to scan the sky in sections. We all don't have the same level of eyesight. Even if we did have the same level of eyesight, and we've been trained in the same way, many studies have shown things vary from person to person. Performance varies from person to person, but certainly people get tired, they get bored, they get distracted, they get stressed. But if we compare that with the AI, as we've shown, like with those 5 cameras, you can actually see the whole sky, and we can see the whole sky 10 times per second. Contrast that with around once per minute, right? The performance of the system is predictable. It's a computer. It can accurately measure where the intruder is. Humans are really not good at that, understanding relative position and motion and altitude and so on. And then I think pretty importantly, the computer system's always on, right? It's always paying attention. It doesn't have a phone in its pocket that it wants to pull out every 2 minutes. It doesn't have a Facebook account, right? So, on the face of it, AI seems a much better, alternative, but how do we actually know it performs so well? So there's a lot of ways that, a lot of different methodologies for measuring the performance of AI systems. I can describe pretty well what we do at Iris Automation to prove our level of performance to the regulator. We basically fly drones with our technology on board at GA aircraft at really precise geometries, altitudes, velocities in different environments, pretty much a daily basis. We've done that over 20,000 times now. And this allows us to gather data to train the system. Remember back to, just like how we teach a baby to understand colors and so on. And then we use ground truth data to prove that the system's estimation of intruder position is actually accurate. And then we mimic these encounters in our vision simulator. You can see that's actually what I'm showing on the screen here just now. You see some images that our simulator that we built to prove, and we can, by mimicking those encounters, we can show that our simulator is accurate in comparison to real life. And then we can scale encounters in the simulator and use things like different cloud cover, different illuminations, visibilities, intruders to demonstrate performance across a whole range of real-world scenarios. And getting all this data has been really key to prove performance to regulators and get various BVLOS approvals without the need for visual observers. Lastly, we've seen a lot of companies start to get approvals, right? We've seen Volaris Aerospace in Canada get SFOC approvals to fly their drones autonomously from their drone in the box. Iris Automation, we've got a bunch of approvals recently, both for onboard and ground-based technologies. I mentioned Census Technologies in the past. Earlier on, working with their customers, they've been able to get a lot of BVLOS and EVLOS approvals for customers using their drones with AI-based detect and avoid on board. So to wrap up, BVLOS is happening. Beyond visual line of sight is happening. It can really, truly unlock the potential of your drones. And artificial intelligence, as it gets deployed more on air taxis and GA aircraft, it will ultimately prevent 2 aircraft from ever colliding in midair again. With that, I would like to thank you all very much for your time today. I'm going to pass back to Amanda. Thanks so much.
Thank you very much, Jason. Our next speaker is Rich Wronski, who serves as Vice President of Sensing, Perception, and Applied Robotics at Charles River Analytics, where he leads a team of scientists and engineers in research and development of the company's sensing and perception product portfolio. He has more than 30 years of program leadership experience. Welcome, Rich.
Thank you very much, Amanda, and thanks to all of you in our audience joining us today. So this portion of today's presentation will be focused on looking forward, particularly towards enhancing trust and resiliency of autonomous teams. So not just single assets, but teams of assets, enabling that collaborative autonomy and the evolving capabilities of autonomous swarms, all considered within a focus of mission level success. So autonomous systems will be increasingly used to augment team capabilities and enhance teams' mission performance going forward. However, widespread adoption of this level of autonomy will require trust in autonomous teammates from their human counterparts. A few key enablers to establishing that trust include things like implementation of explainable AI. This is, in comparison to or in contrast with black box type AI that doesn't offer the same level of insights in the underlying reasoning to the operators that the autonomous system is expecting trust from. So getting to a point where the operator doesn't merely grow accustomed to what an autonomous system may decide, but how it decides that is really important. Use of natural interfaces is also important, so things like automatic speech recognition, natural language understanding, as well as operational manageability. So operator coordination at the mission level, not micromanagement of individual vehicles. So not surprisingly, all of these enablers are similar to what is required for successful human-to-human teaming as well. So we found this through a number of research programs over the years, and are now incorporating this thinking in our products going forward. So increasingly, groups of autonomous vehicles are being used in a collaborative manner to achieve tasks. This is largely driven by the increasing availability of cost-effective, affordable vehicles, increasing computation power on board those vehicles, as well as a greater range of sensors and fused sensing technology. Adoption of open architectures is also important as it promotes flexibility. This is really embodied in the expansion of system capabilities by the use of hardware-software appliques, as well as swappable application-optimized payloads. These open architectures also, very importantly, enable communications across heterogeneous platforms, and we'll talk a little bit more about that later in the presentation. As Jason suggested, that there are a number of limitations, preventing us from realizing some of the full-blown autonomy that's in the works. Obviously, there's ongoing technical constraints that we're working through. The aforementioned confidence or trust in autonomous vehicles, as well as the many operating regulations, FCC Part 107, as well as much of the BVLOS and other regulations that Jason had spoken of earlier. So naturally, this collaborative element leads us to a discussion of swarms. Swarms are largely synonymous with the intersection of multi-agent systems having an ability to self-organize. At Charles River Analytics, we define a swarm as a group of vehicles that are working together and responding to their environment, active responses to changes in the environment or obstacles that are encountered to achieve their mission objective. I think at this point we've all seen, certainly if you're on this call, you've probably seen groups of drones performing light shows, pretty spectacular events, but while entertaining, this is really more of a choreographed display in a very static environment. So we're really taking things beyond that, and that's the focus of our discussion here today. So we're focused on a future in which swarms adapt to both the environment and the evolving composition of the swarm during the mission. We'll talk a little bit more about that as we go forward too. So this involves swarms comprised of different types of vehicles, for instance, in a heterogeneous manner. Also swarms that are given objectives and coordinate their activity amongst the individual members of the swarm, and therefore enable the operator to manage the swarm as a whole rather than micromanaging individual vehicles. It's a very, very important concept. So from an industrial application perspective, there are lots of applications for swarms, be it in agriculture, search and rescue, urban reconnaissance, environmental monitoring, and obviously many defense-related applications as well. So drones themselves are rapidly becoming smarter and more capable. An original assumption that individual robots within a swarm ought to be simple, that assumption is changing rapidly, along with the rapidly changing capabilities of these assets. They can now perceive their world, share their discoveries, and plan their activities towards mission success. These advancements in this computational ability on board the vehicles open a range of new possibilities for swarms. They can operate more effectively in communications denied environments and actually replan in the absence of communications. And they can also allocate subsets of the larger swarms to cover specific tasks as missions evolve. So, allocating individual tasks within the swarm, for example, to patrol versus actual interdiction tasking. So while a swarm is composed of individual vehicles, it is also an entity of its own. Really, operators should be able to say, swarm, find the lost hiker, or swarm, monitor the health of this field. It's really the swarm as a whole that is best equipped to ensure that the mission is achieved. Thusly, interactions with human operators should be between the swarm as a whole and the operator, not between individual robots within the swarm and the operator. Obviously, a lot to be considered there in terms of workload and such. So the more capable these swarms are, the easier they are to manage for operators on the other end. So I mentioned heterogeneity earlier. We often think of swarms as airborne drones. It's certainly a quickly maturing domain for our autonomous systems. But swarm vehicles can have different capabilities. This includes different aspects of locomotion, be it as copters, winged, treaded, serpentine. Depending upon the domain in which they're optimized for operation, be it airborne, ground, maritime, what have you. So sensor packages may also differ significantly. We talked earlier a bit about different payloads. So sensors having different video and imaging capabilities, chem, bio, radiation type sensors, agriculture focused, hyperspectral imaging, things like that. Additionally, effector packages can add a heterogeneous element to the swarm, depending again on the intended mission. So in addition to their physical characteristics, individual vehicles can also be heterogeneous in their health and status. Again, an important consideration when you're thinking about swarms assigned to complex missions. For example, general expected wear and tear, battery depletion, debris getting into the rotors, wheels. They may all impact the status of the individual vehicles. Health-related conditions, such as sensors working at compromised levels. They may have failed entirely. They may be operating in just a degraded state. Speed or maneuverability affected by broken parts, either through normal wear and tear or challenging aspects of the mission itself. But in addition, the swarm itself has an overall health, and this is in reference to its ability to achieve the desired mission objective. So even in the face of individual vehicle failures, if the swarm is outfitted appropriately, it may still be able to achieve its mission if the right contingencies have been put in place, the right planning, et cetera, just as you would a human unit tasked with a particular mission. Okay, a bit now on control of swarms and various models that are applied. We generally think here of centralized versus distributed models. So when is a centralized control model optimal? Well, it's when using vehicles with generally with more limited computing ability, and also when a central system or node will also be connected continuously to the vehicles. Obviously, in this case, reliable communications is necessary. This is really where decentralized control is more optimal. So when that communications may be disconnected or intermittent, or where there's a high risk of single central node failure, either due to health or other obstacles that may be encountered during the mission. Also, decentralized control supports individual vehicles working on very highly localized tasks. This helps from a bandwidth management perspective. So understanding which method is best for a swarm really depends heavily on the centralized, decentralized algorithms being used and the particular mission scenario. I'll say at Charles River, much of our focus currently is on the decentralized swarms, especially in hazardous and comms-denied environments that support the more complex mission scenarios. That said, we also value the practicality of centralized swarms where they may be appropriate, where the conditions are not as variable or unpredictable. Okay. So, how does the swarm actually decide who does what? Task allocation in swarms is similar to multi-robot task allocation. Commonly, robots are evaluated against a function that incorporates a list of tasks and the ability for a robot or a group of robots to perform the next tasks in the list. Assessment of the world state both before and after the robots perform the task is also a critical element. So a variety of algorithms and techniques can be applied here. Unfortunately, we don't have time in today's session to dive too deeply into this, but perhaps in a future webinar. Very interesting topic indeed. So managing the internal swarm communications is a significant task in and of itself. But for large swarms, or rather broadcast communication is suitable for small, very well-connected swarms. But for larger swarms, there's simply not normally enough bandwidth available, or sometimes not enough processing power on the vehicles to handle the broadcast. We certainly want individual vehicles working on their assigned tasking, and as much as they can focus there and only deal with really critical, important messages and status back and forth. That's where we want them focused. So strategies for larger swarms often involve communicating with nearest neighbors, passing along only those globally important messages, using local communication focused on specific tasking, and often deployment of wireless mesh networking, supporting variable or reconfigurable topologies suited to the mission scenario. Swarms may also need strategies for intermittent or denied comms environments. So we're exploring vehicles that can anticipate others' actions with some degree of certainty during communications blackouts, and then sort of pick those back up again when and if communications resume. Again, this enhances the likelihood of mission success even in a degraded environment. So Charles River, our swarm coordination framework facilitates experimenting with and building swarms that offer the greatest range of usability. So this implies swarms, as you see listed here on the slide, swarms that are autonomous, decentralized, heterogeneous, responsive to their environments and environmental changes, extensible to additional ranges of behaviors and readily deployable in support of missions that have been modeled and taken into account in the formation of the swarm itself. So along with many of our partners, we're advancing the state of the art here at Charles River, tackling a variety of challenges in this domain across multiple active program efforts. I've listed a few of them here on the slide. Won't go through each of these individually, but you can read that for yourself. Quite a number of interesting challenges when it comes to this technology, and it's very, very exciting to see this moving forward, and happy to be working with a great deal of sponsors and other industry partners supporting these efforts. So I'd love to hear from those of you in the audience going forward. My contact information is here. If there are opportunities for us to engage in the future, whether you have questions or again opportunities to partner in solving some of these challenges, I'd love to hear from you. So thank you very much for your attendance today, and I'll hand the floor back to Amanda.
Thanks very much, Rich. Our final speaker today is Jeffrey Starr, who serves as the Chief Marketing Officer for D-Fend Solutions. He's a frequent writer and speaker on CUAS and counter-drone topics with an MBA from Harvard Business School. He has held positions in security, public safety, defense, information compliance, and risk management sectors, among others. Welcome, Jeffrey.
Thank you, Amanda, and thank you to SA Media Group and Aerospace and Defense Technology for this great opportunity. I think it's a great to kind of speak next and tie some of these themes together. I mean, we heard Jason talking about the whole beyond visual line of sight concept and situation, and then more specifically drones that have no noise, and all of this as kind of an enabler for new drone applications and new drone use cases. And that a similar theme continued with Rich when he spoke about the proliferation of drones because of the lower cost availability and the increased power of those same drones on each individual vehicle. So again, enabling a whole new set of applications and use cases. Now, what I'd like to do is take those same themes and characteristics and concepts and actually now show how they're also relevant to the other side of the equation, the counter-drone world. And the title here is Control the Drone to Control the Threat. I'd like to kind of present a new emerging point of view as drones go into new environments, as we're talking about sensitive environments, urban environments. We have to rethink the counter-drone world, the countermeasure world, the counter-UAS world, to a world more focused on controlling that threat directly rather than just confronting it. And that kind of sets up the theme. Very briefly, D-Fend Solutions. We're basically pioneers in a new category of counter-UAS, counter-drone called cyber takeover for the most sensitive and challenging environments. We have hundreds of deployments worldwide by top-tier security agencies. We're protecting major events. You can see by all the flags we're in over 20 countries in all continents, protecting all kinds of infrastructure, airports, events, things like that. We've been selected best in class in various evaluations for law enforcement, homeland security, defense type of agencies and environments and demonstrations. We've protected very large complex events. You can see in the pictures on the lower right here, we've been deployed. You can actually Google and find a lot of interesting incidents that we've helped protect, from papal masses to the G7 summit to European football championship games. We're growing very fast. We're pushing 200, close to 200 employees throughout the world. So that's just briefly about us. Now, in terms of the environments, I think we heard a lot from Jason and Rich about the new emerging drone economy and the emerging drone society. And, for all of those use cases and environments and the sectors, obviously, as drones proliferate and contribute great value into those sectors, there's also the potential for risk or accident or danger or nefarious purposes. So you need to think of the counter-drone world in those areas as well. And here just gives you a brief overview of all the different environments, kind of the early adopters for counter-UAS and counter-drone. We're in the defense area, in law enforcement, airports, VIP protection, national and homeland security. But then, there was a second wave where we saw, as drones continued to proliferate in other sectors, the demand for counter-drone solutions in maritime and border protection in government buildings. And then now we're actually seeing more demand from even more sectors, things like prisons and enterprise stadiums and arenas and more. And we'll give some more specific examples about why that's happening. And here, all you have to do, any given day now, there's lots of incidents in the news. Lots of drone either attacks or accidents or risks or something that's in the news. Actually, and if you want to go to our website, we have something called a drone incident tracker where you can sort and filter and research all these incidents. And I won't repeat all of them. You can just listen to the news any given day. But, for example, at Reagan National Airport in D.C., a few weeks ago, there was a drone incident that delayed flights. There's constantly in the news issues of people using drones to smuggle things into prisons. There have been obviously the need to protect VIPs from drone attacks, smuggling things across borders. And just in the last few days, in the National Football League, there were a couple of drone incidents in baseball games as well. So the list goes on, and it's really incidents happening across many, many different sectors. Now, what's driving this proliferation is not necessarily the big, dangerous military state actor drones, but rather on the opposite side of the spectrum, commercial drones that are becoming proliferating for all the reasons we heard from the first two speakers. They can be easily bought, easily built with do-it-yourself components, and they can be weaponized. They become the new flying IED, improvisational explosive device, if you will, but of the sky. These are commercial. They cost less than $1,500, or they can be built easily from off-the-shelf parts. And that's a theme you're seeing a lot. Just in the last few weeks, you can see some headlines from The Economist, The Wall Street Journal, and the Financial Times about Costco drones being a threat to military, about consumer drones changing warfare, about drones being empowered by state actors, but commercial drones for various threatening applications. So this weaponization of cheap and commercial drones is what's changing the whole counter-drone arena. And different drones represent different threats. You can imagine, here's just a small example, whether it be a direct attack. We're not only talking about nefarious users, we're also talking about careless or accidental situations, people playing with drones near where they shouldn't be and things like that, potentially causing collisions, smuggling of contraband, spying, espionage, and just simple harassment and nuisance are just some of the types of drone threats that are emerging with the proliferation of these commercial drones. And what we're really focused on is, okay, what makes a drone the most dangerous? What is the convergence of characteristics or factors? And you can see here it's a combination of a number of things that are happening rapidly with commercial drones. They're traveling longer distances. They're becoming easily accessible. You can buy them on the internet with very low cost and heavy payload. They can increasingly carry heavy payloads. And the cusp or the convergence of all those together is what's really driving the risk. And this cuts across many different possibilities or scenarios, use cases, if you will. We're talking about just purchasing the drones, and now they're, as I mentioned earlier, they can carry high payloads. They have very sophisticated protocols. They can go long distances. Same thing can be done with do-it-yourself drones from off-the-shelf components. And so kind of they represent the major threat. You also have Wi-Fi drones, which is a kind of different, smaller, but also potential threat. But we really, you have to, with a counter UAS strategy, focus on the major threats, prioritize on those that can travel long distances and, carry heavy payloads. But you need to do that prioritization. Now, what's new? What's different? There have been some amazingly successful technologies in the counter UAS arena that have been tried and true for many years. Now, they came typically, as with a lot of these innovations, from the aerospace and defense environment, from conventional battlefield applications, if you will. They're tried and true. They've done a great job. They've performed incredibly well, but they do have some issues in urban environments or sensitive environments where drones and UASs are now coming into those environments. And it's not just a question of transferring the traditional counter UAS technology over. I'll briefly kind of go into some of those issues. When you think about detection and all the different technologies around detection, you have radar, you have optical, you have vision, you have directional finders, based on RF, and you have acoustic sound. But for some of the reasons we heard earlier, each of those has issues in an urban or sensitive environment. Radars many times detect or pick up false positives. We've seen many situations where a radar is unable to distinguish between a bird, for example, and a drone. As Jason mentioned, there's line of sight issues. So many of these technologies on the optical side require a clear line of sight, which isn't always available in an urban environment or a mountainous terrain. You may not pick up the right locations when you're triangulating on directional finders. And acoustic, as drones become quieter, which Jason also touched on, and as environments become noisier at an airport or a stadium, they increasingly fall short or have challenges as well. On the mitigation side, it's even more extreme, the challenges. Typically, and I'm in the limited time, I am oversimplifying, I'm generalizing, but in a general way, they kind of fit into two categories of mitigation. Any kind of jamming, whether it be radio control jamming, GPS jamming, anything that disrupts the connection between the controller and the drone, and kinetic meaning anything physical, shooting it down. And that might be with a laser, a magnetic field, a bullet, an artillery, a net, a drone killing drone, whatever it is, but something physical. And there, of course, you have major issues on both of these. Jamming, first of all, is temporary, so it's only valid while the jamming is in effect, and that can't be forever. And then the pilot, of course, can regain control. But more importantly, jamming can cause operational disruption, communications disruption. It can disrupt other communications that are essential. And on the kinetic side, you have the potential for collateral damage, either from the projectile itself, if it misses the drone, or even if it hits the drone and the projectile are going to fall down somewhere on something or on somebody. And so there's all kinds of risks as it relates to kinetic solutions as well. So now, as they go into a new environment, our point of view, we're advocating next generation approaches. So on the detection side, RF cyber detection, and to making sure it's fast, it's accurate, without false positives, no line of sight required. And on the mitigation side, an actual takeover. I'll talk with that briefly about that, what that means. But basically, to disconnect, take over, take control of the rogue drone. That's, again, taking control of the threat by taking control of the drone and leading it on a safe route to a safe landing. Key benefit here, continuity. No disruption in communications, no collateral damage, no stoppage in whatever the operation or activity is. This is the basic idea. So the idea of a technology like this is a next generation approach. Take over the technology, detect and take control, land safely in a pre-designated safe zone. Non-jamming, non-kinetic, no line of sight. And so what does that mean? What we like a metaphor of the incident life cycle, a rogue drone incident life cycle. How does it play out? Well, typically, and I'm kind of accelerating it here, but detect and alert, obviously you must first detect the rogue drone. And then from that point on, you want to locate and track several items, not only the drone itself, but the takeoff position of the pilot, the home position, if you will. You need to identify that drone. Is it a friendly authorized drone? You don't want to disrupt that. What is the type? What is the make? What is the model? What is the protocol? And at that point, things converge. And what we're advocating is you really want to go towards a more controlled and safe outcome, where you can either simply, for whatever reasons, maybe regulatory, maybe operational, you may just choose to fend off the threat, meaning send it back where it came from, or actually take control and land the drone, with appropriate authority and approval, as opposed to more uncertain outcomes, where you're shooting something or where you're jamming something, where you may succeed, but even if you succeed, you may not get continuity. An incident will still become a major incident, or worse, the mitigation will be unsuccessful. So in both of those cases, even a successful mitigation could create some, operational disruption issues. So the life cycle of a rogue drone incident is kind of a useful metaphor for comparing technologies. As we again heard from the earlier speakers, the skies are proliferating with all kinds of authorized, friendly, approved drones with greater capabilities. Some of them are authorized, but some of them may not be. Some of them are friendly, some of them are hostile. And they're playing this increasingly critical role. So it's very important that your counter-UAS strategy have the ability to distinguish between these authorized and unauthorized situations and ultimately enable continuity. So again, this new generation technology is RF cyber, where on the detection side, you can have a fast location, ID the drone itself, all these characteristics you need, but in a passive way, a surgical way, dealing with some of the massing issues that we heard earlier, swarming. But again, the goal being no collateral damage, being able to do this in a manual or autonomous mode, but being able to deploy rapidly for these situations. And that's also the other important aspect here is there's many different use cases, many different situations, many different environments that different actors may need to deploy with. So it may be on a military vehicle, it may be covert, it may be tactical, ground level on the move, but may have to set up a situation, on top of a tall building or on a mountain. You may have to protect corridors, like at an airport. So therefore, the airspace needs to be protected with a long-range directional approach. Or you might have also high to altitude, but on a stationary way. So those are kind of the deployments. But the other thing that a counter-UAS strategy has to take into effect is not only worry about the drones that are on the market today, but to be a drone, what we call always a drone threat ahead, and constantly be updating your system for rapid response as new drones, as new technologies come out on the market, being able to anticipate the unpredictable and proactively building and being preemptive and ready with that. So I wanted to stay in the time frame, but basically conceptually we're talking about a new counter-drone world based on 4 concepts that lead to a 5th outcome: control the drone to control the threat, safety, safe outcomes, safe airspace, continuity, focus on the real risk, the most dangerous drones, and then a future of always staying a drone threat ahead. But all of these together get not only safety and control, but ultimately bring continuity. And so an incident doesn't become a incident, if you will, and that so communications, transportation, commerce, and everyday life could continue. So that's kind of a vision of a new counter-drone world to deal with all the positive drone proliferation and new applications and activity that we heard from Jason and Richard. So if you have any questions on that, you can certainly contact me. Jeffrey S. at D-Fend Solutions or info@D-Fend Solutions or visit our website. But thank you again, Amanda, for this opportunity.
Thanks so much, Jeffrey. Before we move on to our Q&A section, I would like to take a moment to again thank our sponsors, Cinch, Eagle Picture, Maxon, Sea Level, and Siemens. Their support made this webinar possible. As a reminder, you may download PDFs of sponsor technical papers under the Event Resources tab on your screen. Also note, you can still submit questions for our speakers through the Ask a Question box. Now let's take some that have already come in. First up, to Jason, in reference to see, detect, and avoid, do you also characterize the target craft with signature, evaluation, and threat level?
Yeah, thanks for the question, Edmund. So basically what we do when we detect something else in the airspace is we understand its position and its position relative to, you know, the drone, or if it's a ground-based system, relative to that ground-based system. And we understand what direction it's moving in, whether it's coming towards us or moving away from us, you know, and also its altitude, and its classification, right? Is it a small plane? Is it a helicopter? Is it a bird? Is it a multi-rotor? And so these things can be used to determine, you know, how you actually react to it. Now, and so yes, we can, you know, all of those come together to determine the threat level, right? So for example, if you're flying a drone, you don't really care about flying into a bird so much. The bird is going to move out of the way. But if you're in, you know, an air taxi, or if you're in a helicopter and you have you know, one of these systems to detect air traffic on board, you most certainly do want to avoid large birds, right? Because I think we've all seen the images of what bird strikes can do to helicopters and other aircraft. Then I think, you know, particularly when I went through the presentation, I showed a situational awareness tool by a company called Kongsberg. You know, there's lots of other similar tools out there. So, you know, Drone Sense, OneSky, and several others, and they allow you to take the input from systems, you know, like you know, electro-optical, artificial intelligence-based detect and avoid, and radar, and, you know, ADS-B, and use all of these things to make decisions as to how you want to react to any particular intruder aircraft. So, you know, based on the altitude, you may want to ignore it, or, you know, based on its classification, you might want to ignore it. Yeah, so absolutely, we use and can use a variety of factors to basically determine the risk profile of any specific intruder.
Great, thank you so much, Jason. Next up to Rich. To support dynamic use of swarms, where is the technology today to support initiatives that will utilize swarms, and how does that translate to evolving regulations and certifications?
Great question. The simple response really is I think the technology itself is moving much faster than the regulations you know, required to operate. And I think, you know, I spoke quite a bit about trust in autonomy. It's not even as much a technology driven at this point as it is the human driven, and you know, achieving that level of trust that then helps drive comfort and the appropriate regulations and certifications around it. So they really go hand in hand, and there's a human element there that I think always sort of lags the technology. So I hope that answers your question. But it really is amazing at the rate at which technology is evolving. The mere fact that we're talking about some of these things now, when only a few years ago they were still science fiction to some extent. It's a tribute to how fast things are moving. So.
All right, great. Thank you so much, Rich. And next up to Jeffrey. Are there solutions for situations that require multiple counter-drone systems to cover a vast area but have limited resources to operate separate systems?
Yeah, definitely. I mean, you can. The strategy there is setting up sort of a multiple sensor C2 or command and control system, or interfacing with such a command and control system. If you need to secure a large area, you can do that with in a more centralized way with less resources by using such an approach and safeguarding a more massive area. So basically, you can integrate your counter drone system either with or a third party command and control system, and this fusion enables operators to view drone information on kind of a map-based command and control platform with different options to trigger mitigation via, with the platform and kind of expand your operational awareness beyond just, one operator protecting a specific space. So there are definitely ways you can scale up and integrate into larger command and control systems to expand that situational awareness for the tactical team.
All right, wonderful. Thanks so much, Jeffrey. Well, with that, we are at the end of our webinar. I would like to thank Rich Vronsky, Jeffrey Starr, and Jason Hardy-Smith for their presentations, as well as our audience for joining us. And thank you to everyone who submitted questions. We'll work with our speakers to follow up with any that went unanswered. As a reminder, you can download a PDF of today's slides and technical papers from sponsors under the Event Resources tab on your screen. In just a moment, a survey will pop up. Please tell us what you thought of our program by answering these 3 questions. This webinar will be available on demand for the next year, and an email will be sent to everyone who registered as soon as the archive is ready. Once again, thank you for watching.